Have you ever written some code and just had that gut feeling that it could be, faster? That's a good instinct, but in computer science, feelings aren't enough. We need proof. So today, we're going to dive into a really precise method for counting the actual cost of your code, so you can prove, objectively, which way is better.
So, let's set the stage. This is a question every single programmer runs into. You've got two different functions, and they both solve the exact same problem. How do you prove which one is the winner? We can't just guess, right? We need a system. We need a reliable way to measure their efficiency.
And that system is called the frequency count method. It's actually pretty much what it sounds like. We're going to go through our code line by line and literally count how many times each statement gets executed. Once we have all those counts, we just add them up and boom, we get a simple function that tells us the total cost of our algorithm.
So here's our game plan for today. First, we'll talk about why we're counting steps and set some ground rules. Then, we'll start with something simple, analyzing a single loop. After that, we'll level up to nested loops and even tackle a tougher n-cubed challenge. We'll also see how this isn't just for time. You can count memory too. And finally, we'll wrap it all up with the key takeaways you need to remember.
Okay, first things first. Before we can start counting, we need to establish the rules of the game. This is the foundation for everything we're about to do.
The core idea here is really simple. We're going to say that any basic statement, like creating a variable or returning a value, costs 1 unit of time. Our mission then is to figure out the frequency, or how many times each of those statements runs. We add all those frequencies together, and that gives us a total cost function for the entire algorithm. Simple as that.
All right, let's get our hands dirty with level 1. We're going to start with a classic programming task, just summing up all the numbers inside an array. Here is the code we'll be analyzing. It's a pretty standard sum function. It takes in an array, which we're calling A, and n, which is just the number of elements in that array. Inside, we create a variable, s, to hold our total, starting it at 0. Then we loop through the array, adding each element to s. And at the very end, we return the final sum. Now let's start counting.
Okay, let's break this table down. The first line, int s equals 0, that only happens once, right? So its frequency is 1. Same for the return s at the end. It runs just once. The line inside the loop, the addition, that's going to run exactly n times, once for every element. But hold on, look at the for loop itself. Why is its frequency n plus 1?
This is a really important point, a common place where people get tripped up. Think about how the loop actually works. The condition I less than n gets checked when I is 0, 1, 2, all the way up to n minus 1. That's n successful checks. But then I becomes n. The code has to check the condition one last time to realize it's false and that it needs to stop. That final failing check is that extra plus 1. So n passes plus 1 final fail equals n plus 1.
Now we just do the math. We add up our frequencies, 1 plus n plus 1 plus n plus 1. That gives us a total cost function of f of n equals 2n plus 3. Now, in what we call complexity analysis, what we really care about is how the algorithm behaves when n gets huge. If n is 1,000,000, that little plus 3 doesn't really matter, does it? The part that grows and really defines the cost is the 2n. So we simplify this to its order of complexity, which is just order of n, and we write it as on.
Awesome, you've got the basics down. Time for level 2. We're leveling up the difficulty a bit by looking at nested loops. Our problem now is to add two matrices together. This means we're going to have a loop inside of another loop.
So here's the code. We have an outer loop with I that goes through the rows, and an inner loop with j that goes through the columns. The most crucial thing to understand here is that for every single time the outer loop runs, the inner loop has to run completely from start to finish. That's the key.
Let's apply our counting rules again. The outer loop, we already know that's n plus 1. Now for the inner loop. It runs n plus 1 times, but it does that for each of the n times the outer loop runs. So what do? We multiply. It's n times n plus 1. And that addition statement in the very middle, well, it runs once for every column, n, for every row, n. So that's n times n, or n squared.
So when we put all of that together, we get a function that's roughly 2n squared plus 2n plus 1. And here we go again. What's the most important part? We look for the highest power of n. In this case, it's 2. That n squared term is what really drives the cost. So the complexity is order of n squared, or
O of n squared.
Okay, time for the final boss, level 3, the n-cubed challenge. We're going to look at matrix multiplication, which, as you might guess, needs 3 nested loops. Now, based on the pattern you've seen so far, take a second and predict what you think the complexity is going to be.
If you guessed O(n) cubed, you are absolutely right. The pattern continues perfectly. The cost of the middle loop is multiplied by n from the outer loop. The cost of the innermost loop is multiplied by n squared from the 2 loops it's inside of. And that single statement tucked away in the very center, it runs n times n times n, giving it a grand total frequency of n cubed.
Adding it all up gives us a big function, but the term that matters most is that n cubed term. Everything else is small potatoes in comparison. So the time complexity is order of n cubed, or O(n) cubed. See the pattern? Each level of nesting just added another power of n to our complexity.
Now this is really cool. Time isn't the only thing we can measure. We also care about how much memory or space our code uses. And the great news is we can use the exact same counting logic to figure out an algorithm's space complexity. But instead of counting operations, we just count the variables and data structures we create.
Take a look at this comparison. For our first 2 examples, the time and space complexity were the same, O of n and O of n, O of n squared and O of n squared. But look at matrix multiplication. Something really interesting is happening here. The time it takes is O of n cubed, but the memory it needs is only O of n squared, since it just has to hold the 3 matrices in memory.
And this leads us to a really important insight. An algorithm isn't just good or bad. It's all about trade-offs. Our matrix multiplication algorithm is slow. It takes a lot of time to run, but it's actually pretty efficient when it comes to memory usage. So let's zoom out and look at the big picture. We've gone from a single loop to triple nested loops, and we've even talked about memory. Let's wrap this up by summarizing the absolute key rules you need to take away from this.
Here they are, the golden rules. Remember these. Number 1, a simple statement is always just 1. Number 2, that standard for loop check runs n plus 1 times. Number 3, when you nest loops, you multiply their frequencies. And finally, to get the order of complexity, just find the biggest power of n, and you can pretty much ignore the rest. You might be wondering, why do we get to just throw away all the other parts of the function? It's because we're thinking about what happens at a massive scale. Think of it like this. If the n cubed term is an elephant, then the n squared term is a cat, and the constants are like mice. If you're weighing all of them together, the elephant is all that really matters, right? The highest power term always dominates the performance in the long run.
And there you have it. We've given you a powerful tool, a way to measure, to count, and to compare your code. You don't have to guess which solution is better anymore. Now you can prove it. So I'll leave you with this question. Now that you have this knowledge, how is it going to change the way you write code?